Check. All right, everybody. Hello and welcome to another edition of Ask Us Anything About Electrochemistry. I'll be your solo host today. I'm Dr. Neil Spinner with Pine Research. My esteemed colleague Alex is out today, so it'll just be me. Thank you for joining me, for those of you who are joining me or watching this later. Just a few notes before we get started here today. So this is an episode of, as I said, Ask Us Anything About Electrochemistry that we like to do here once a week on Fridays. We do this because at Pine Research, we get a lot of questions and we get a lot of emails, and we visit customers and we travel around and we get a lot of questions about electrochemistry, as you might imagine. And so we started this, it's been a few months now, as a means to try to answer some of these questions and give everybody an outlet to ask some of those questions that maybe you're feeling scared to ask or don't know the answer to, or you're not really sure where to turn. We're trying to be a resource for those of you who are in graduate school or postdocs or whatever stage of your career, and you're trying to get a grasp on electrochemistry. It's a very common thing to be feeling like you're lost, I think. And so hopefully we are able to provide a resource for you if that kind of describes you in any way. A shout out to our YouTube members. Thank you for those of you who are members of our YouTube channel. There's a lot of content that's available to you, including previous webinars that I've given. And if you rewind this to a few minutes ago, if you weren't with me, we are releasing a podcast, and YouTube members are going to get early access on December 7th, I think it is. So our podcast will be releasing in December, and then on platforms wherever you can get podcasts in early January. They'll be more publicly available. But if you want to get early access to our podcast, encourage you to join our YouTube channel. Just the last couple of things, again, is that just to sort of reiterate, if you're doing electrochemistry and you want to ask any questions, I just want to encourage everybody to ask those questions, even if you feel like they're dumb or you're scared or you wouldn't dare ask your advisor those questions. I'm not looking to judge anybody. We're not looking to make anybody feel badly. We're happy to try and answer any questions, even if they're silly, you think they're silly or basic or anything like that. And then the last bit is that apologies in advance if I mispronounce anybody's name, but this is YouTube, and I only have your YouTube handle account name, to go on. So that's all I really have with which to try to pronounce and work through. So, and also shout out if anybody is watching on Twitter or X. I believe we are live streaming there as well. And I don't think as of yet, or at least at all, maybe we've quite figured out how to get X Twitter users to like communicate or chat. I'm not sure that feature's there, or at least we haven't really figured it out. So if you are watching on Twitter or X and you wanted to ask a question, head on over to YouTube and then use the chat feature in YouTube to ask any questions that you might want answered. So actually, I think earlier today there were a couple of questions here from Bob Owl. So Bob, if you're watching this now or perhaps later, I can get to your questions. I think you were sort of first here chronologically at the very least. So I'll try to kind of get into these questions a little bit. So Bob had asked, I'm running an OER experiment, so that's oxygen evolution reaction. My purpose is to get a transport overpotential by subtracting activation overpotential and ohmic overpotential from total overpotential. This is actually a concept that I wasn't overly familiar with. This sort of, I don't know, kind of aggregate summed overpotential, and you're subtracting parts from it. So I did learn a little bit about it in the time here before the live stream. Also, I'll talk about it a little and give you a little bit of examples here. And I think I kind of understand where you might be going wrong or what you might want to try to look into. So anyway, here there's a few parts to this question, and then again, I'll sort of dig into it here. So Bob says, but I kept getting negative transport overpotential. I want to know what the problem is here in this process. So the last two bits that he commented here are, I obtained the activation overpotential from Tafel fitting to the overpotential as a function of the log of current density. Okay, that's typical Tafel slope. And I measured an uncompensated solution resistance by EIS. Multiplying by the current, I gained ohmic overpotential. Lastly, by subtracting the two overpotentials from the total overpotential, I got negative transport overpotential. Okay, so there's a lot of saying the word overpotential here. So if you're sick of hearing overpotential, this is not the podcast or live stream for you, because I'm probably going to say it a lot here. But first of all, what's the problem? Okay, so there's a lot of things here, and in short, it seems to me the only thing of the processes you described that I feel confident in is getting the uncompensated resistance from EIS. Everything else you're doing is very possibly a source of error or the source of error with what you're trying to calculate. So first of all, just as a point of clarification, from what I found anyway, is that you have overpotential. So overpotential, I can kind of try to draw some of this as well. Let me just pull up PowerPoint where I can draw. But basically the point here to make is that overpotential is sort of just loosely, it is described as the difference in potential between the process, the process under study, I guess you would say, and your actual potential. So like, my good friend Alex is a better artist than me, so you're gonna have to bear with me. But like, if you're thinking about some process, and I have a peak, so if I think about a CV with like a regular looking duck, that's not too bad, right? I guess one side is bigger than the other. I'm not the best here. Okay, so if you consider, for example, this is the cathodic peak, and this is the anodic peak. Typically what people do is they consider that the E0, sometimes sometimes it's down here, sometimes it's zeros at the top. But in any case, that's roughly speaking halfway between the peaks, right? And for a normal process, you might have 60 millivolts of shift. But let's just say this typical kind of situation is going on, right? Now this is OER, so okay, fine. The potential is probably higher, but I'm just trying to make a point about overpotential here, right? So overpotential is described as E minus E naught. Okay, so basically, overpotential is just what it sounds like. The potential of your process that you're studying, the redox, the Faradaic process, how much over that you are. So if this happens at 100 millivolts and I'm applying, 200 millivolts of applied, my overpotential is 100 millivolts. I have 100 millivolts like more potential than the process is at or whatever. And so generally speaking, you can think of this as like a driving force. The more overpotential, the more you're driving your process, the stronger you're driving. And then you get into things like the kinetics increases and the mass transport, et cetera. And that's where these different overpotentials are coming from. So generally here, the idea, again, based on your question, is that you're sort of making the assumption that the overpotential is also equal to the sum of, let me get your terminology here, which is trying to get a transport overpotential, activation, and ohmic. So you might have an ohmic overpotential. This is like uncompensated resistance. You have what you're calling an activation. I'm going to call it charge transfer because I've seen that actually in a publication. Activation / charge transfer. This is basically like you'd say like a kinetic overpotential or something like that, plus transport overpotential. And so you're trying to isolate this one by subtracting these two. Okay. Now here's the couple of points I'm going to make. First of all, actually, in truth, you're trying to get this last one. So what you're actually doing is you're taking this one and you're subtracting this one and you're subtracting this one. Okay, well, here's some problems. First of all, you're doing OER. Okay, so OER, let's just say, you go to a high potential and your current increases. Where are you selecting? Are you picking sort of arbitrarily? Because you're saying when you do this subtraction, you get a negative overpotential. Well, where are you picking? Because frankly, if where the OER happens is not exactly clear. It's sort of at the onset of where this potential starts to curve up usually. So that first of all matters where you identify as where's the onset of OER, like which of these potentials is it? That's one thing that's not trivial. You have to pick that because that determines like your E0, which determines your overpotential. Secondly, where is this? Are you picking this point? Are you picking this point? Where you pick will affect this calculation, right? Where you pick this value of just your actual overpotential, your raw overpotential. So that's the first thing. Could be an error, but depending on where you pick, it's going to make a difference. Now this here, as I said, you're doing EIS, okay? And you're getting your R, like your uncompensated resistance. So R0, R ohm, whatever you want to kind of call it. And then you're just basically using Ohm's law. So V is equal to IR. Okay. Now, again, this calculation of the ohmic resistance using EIS, high frequency intercept, something like that, probably pretty solid, probably good. But what current? Again, where is your overpotential? You're picking here, you're picking here, you're picking here. This is the current. This is the potential down here. Well, what current are you multiplying this by? You know what I mean? This voltage here, you're basically saying is actually n ohms. Eta. It looks like an n. You know what I mean? I always think of it as n. But your ohmic overpotential is that resistance times current. But what current? You say you multiplied it by current. Well, you're probably picking some arbitrary current. Or is it the background current here? Or are you picking a current over here? Like, to me, this is not clear exactly which current you're picking. So that's the second point of contention, I would say, where error might be happening. Now, the last one is related to this charge transfer. And this is because you say activation. whether it's activation or charge transfer, overpotential, okay, will affect this calculation. Okay, so first of all, let me share my software and I'll talk through this one. And then there are a few questions coming into the chat that I will certainly get to as well in just a moment. Nope, where is it? There it is. Okay. So if you have, for example, you're trying to calculate the activation or the charge transfer, which is like a kinetic parameter, the overpotential, the component of your overpotential that's related to charge transfer. You say that you got it from a Tafel analysis. Okay. So my first comment, and this is if you've ever joined me in these live streams before, you might be aware that one of my like electrochemistry trigger points is Tafel analysis. And this is the third thing, I guess, of the first two I talked about previously. This is the third thing that is possibly a very big source of error. You may very well be inappropriately applying Tafel analysis, a Tafel slope, a Tafel plot, everything. So a Tafel plot, I have some sample data from the plot that I'm showing you right now. So like in this case, I did rotating ring disc electrode kinds of tests, and you get limiting currents. You can separate kinetic and diffusional information. I don't know if that's what you did or are doing. It's not really easy to do that with OER, as is perhaps with ORR. OER doesn't always really make a nice plateau, so it's not quite easy to do that always. But a kind of Tafel plot might look something like this. I didn't put units, so forgive the lack of units here. This is like millivolts on the y-axis. This is log of current or decades of current on the x-axis. So now basically what you might be doing, you say that you use the Tafel slope to get your activation or your charge transfer overpotential. Again, where did you pick? Now, what's somewhat common is that people apply a slope to this. So they'll put like a baseline, you get a slope, and you're looking for like, sometimes you're looking for that like 60 millivolts per decade, so, or 90. So you can see slope, like this is millivolts. So it's like 90. You might find the place where it's 60 millivolts per decade, or 120 millivolts per decade maybe is more of a one electron process. So there you go, 120 millivolts per decade. It depends on how many electron process it is, right? I'm glossing over a lot of specific Tafel analysis on purpose here, but my point is that even Tafel analysis is very much very often a subjective process. Where are you applying your tools? Where are you taking the slope? And even then, where is the overpotential you're identifying from your Tafel analysis? And the second thing, which is actually more the first thing that I mentioned, which is why I have a real problem with Tafel analysis, it's very possible what sort of theoretical basis do you have for transforming your data into a Tafel plot? Because a Tafel plot comes in the Tafel equation is derived directly from the Butler-Volmer equation, which is a purely kinetic equation. It describes only kinetics in the absence of mass transport or anything else. So fundamentally, you cannot really take just plain like LSV data or CV data from your OER reaction and make this plot, because this is actually not log of current on a Tafel plot. It's not decades of current. It's decades of kinetic current only. It is a kinetic information. And so that is, I forget what I'm at here, third or fourth possible reason as to why you may be having a pretty severe error in your calculation. So, so Bob, if you're watching now, or you come back and later watch my answer to your questions, I hope that is a decent set of propositions for you related to your inquiry. Okay, so I would look at your data very carefully and consider how any of those possible things are impacting that calculation, because very likely this negative overpotential you're getting is just a consequence of a 3 or 4 different assumptions that are being made possibly improperly, leading to errors in the calculation of these different various overpotentials. So give that a look and see what you have, what you conclude, I suppose. Okay, so let's see. I see a question from Shuaib Malik, who says you want to learn EIS model fitting. That is certainly a bit of a loaded question and a big question. It's not easily something I can show, instantly. I guess in a live stream like this, if you have a more specific question, I can try to address it. I can try to bring up some data with my software here and show you kind of like a couple of example circuit fitting data sets or something like that. But really, if the question is like, help me do circuit fitting, that's really a way too large of a question to answer. That is, first of all, circuit fitting impedance data really is something that takes practice, and it just takes time. You really have to learn. You have to give it a try yourself with whichever software you're using. And then as it relates to your specific data, you will need to, it would help, for example, if you're asking a specific question, for me to specify what kind of data you're looking at and everything like that. Let me put a pause on that for a moment and see. AJ has a question here. Let's see here. If a membrane allows protons and electrons to pass through, and how can we measure and differentiate it? So I don't know that a membrane allows electrons to pass through. Like Nafion, for example, allows protons to pass through. That's basically its function, right? So like Nafion is the most popular or common membrane for fuel cells and like acidic PEM, proton exchange, hence the proton exchange, the name, membrane for that. But a membrane isn't really designed, or shouldn't, I suppose, facilitate the passage of electrons. If a membrane allows electrons to pass through it probably isn't a very good membrane. The purpose of a membrane in most conventional electrochemistry setups, it does that under degradation case. So when the membrane degrades, it starts to conduct electrons. Now, I know that some polymers can be electroactive under certain conditions, like polyaniline, or I don't know. There's probably a million of them, to be honest. So it's not like I'm not an expert on all the different electroactive polymers. But I do know that there are some that, for example, if they have carbonaceous sorts of materials or additives or whatever, they can conduct electrochemically. But for example, in a PEM fuel cell or in a battery, if your membrane ever conducted electricity, like, it's over, because you immediately you'll short, whether it's like what you'd call like a hard short or a soft short, or just like the degree of short. But like, right, the point of a fuel cell, right, or a battery. Let me erase this for a second here and just kind of sketch out a point of this, right? Like, the point of a battery or a fuel cell, if I have my membrane here, this is membrane, and I have my, whether it's a fuel cell or a battery, kind of doesn't matter actually, but I have my anode over here and my cathode over here. I have, whether it's protons or it's some negative ion, it doesn't matter. The point is that the membrane is permissible to ions, right? It's what we would say is ionically conductive, not electrically conductive. And that's key, because we connect the anode and the cathode externally. So if positive is moving this way, that means that either positive is moving the other way or negative is also moving in the same direction. So that would complete the circuit. So basically electrons are moving this way. So it's like if electrons can also go straight through, we don't need this pathway, because this pathway is a potentiostat, or it's your phone, it's your laptop, it's whatever thing is being powered. That flow of electrons in the external circuit is what is giving you the power. That's what you right. And so, what more direct pathway could there be for these, for the anode and the cathode, for their electrochemical half reactions to occur, if than for the electron to go straight through? Right? I mean, that would be the quickest way, but it would also mean your device is useless, because you just have some reaction happening here and some reaction happening here, but you're not getting any energy into it or out of it. Like, there's no real purpose to it. And also, practically what that would mean for like a battery is that it would probably explode. I don't know if a fuel cell would exactly explode, but it's not, you know, it's not ideal if the electrons can go straight through it. This membranes are supposed to be electrically insulating while ionically conductive. So, um, I guess if your question is like, how do I measure that? My guess, like, if after time, let's see. Sorry, the next follow-up is, assume that a sample allows the conduction of protons and electrons. How can we differentiate it? Honestly, I don't have experience with this, which is very possible. And I might not know 100% the answer to this, but my guess is if you have a membrane that conducts protons and electrons, and you're trying to run any of those kinds of systems like a battery or a fuel cell or a separated cell, it's going to be complete trash unless the rate of electron transfer through it is very slow. Like, you're just, electrons are like water, they follow the path of least resistance or least impedance. And if they can go straight through the membrane like I just drew, that is the path of least resistance. If the electrons are going of their own accord, you're not measuring them. So if you have a potentiostat connected, it's not measuring anything. Potentiostat can only really measure the current and the potential because it's going through the potentiostat circuitry. Well, if the electrons are going directly through, they're just like, buzz off, potentiostat. I don't care. I don't even need you. So my guess that the answer to your question, how can we differentiate it, is that a membrane that doesn't electrically insulate gives you terrible results or no results, I guess. Like, you would see a short. It would immediately, like if it's a battery, it would immediately discharge completely, because when it's charged, it has stored energy. And only by connecting it to an external circuit, potentiostat, power supply, something, can you change the voltage to cause current to flow through the external circuit. It causes it to discharge, you get power out of it. But that is a like energetically favored process to like discharge. And the only thing that stops it from happening is the physical separation of the anode and the cathode. Well, that happens because they are electrically isolated, mainly through the membrane. And so if the membrane isn't electrically isolating them, it's just going to self-discharge until it's gone. And then you can't do anything with it. You can't charge it back up, because as soon as you charge it back up, the energy dictates that it just immediately discharges. So, I don't even understand how or why you would use a membrane that has properties like that, unless it's just one of, like you said, it's one of those hazards of degradation. Like, oh well, as it degrades, it starts conducting electrons, and that's not good. You're going to want to try to avoid using a membrane once it's electrically conductive. Yeah, it's not really going to do its job electrochemically. You're gonna probably have a ton of issues trying to use a membrane with those properties. Okay, let's see here. Anuradha has asked, Would it be possible to do IR correction simultaneously with a constant current and constant potential accelerated accelerated stress test in RDE? If so, which IR correction method is better to use? Let me think about this. You're using a gamma ray potentiostat, which scripts that I have to use? Okay, so regarding the gamma ray potentiostat and scripts, I can't help you there, unfortunately. Gamma ray is a great company. I have nothing bad to say about them, but it's not my company, so I don't know the specifics of their software language and scripting and methods and things. So you might have to speak with someone from Gamma about like how physically what to click in the software, and I don't know the answer to those questions. But let me sort of think through this again. So IR correction simultaneously, it should be possible to do IR correction. So I mean, I can only sort of speak for my company, but um, you can do IR compensation, IR correction. Let me just sort of let me sort of pull up something to show you. For example, and again, this isn't going to help you with your gamma ray specifically, but perhaps they have a similar analogous kind of a situation. So, like if you have a bulk electrolysis, so let me again take a look at it's a constant current and constant potential accelerated stress test. So an RDE. I'm assuming you do sort of like steps of this, like you hold the current constant for a while, measure the voltage, and then you potential, and then you hold the potential for a while and measure the current. I don't know exactly. You usually stress tests are like repeated cyclic voltammograms. So I don't know exactly what this kind of this test entails precisely, but let just make assuming. Sorry, I have it up now, right? Yes. Okay. So, like, for example, if you have this is a version of we call bulk electrolysis. This is a more general term for apply something and measure something. So, constant potential or constant current. So, if you do a constant current and you apply however many microamps you know for 6 years, probably a little less than that, but that would be fine. You can, for example, apply IR compensation, either an automatic amount if you calculate it like through impedance or something like that, or a manual. You can put however many ohms to compensate for, and you can do the same for potentiostatic mode. Again, this is with our software, so for sure it's possible to do that. Um, uh, you know, which method is better to use? So to that point, I don't know exactly what you mean. If what you mean is what method of IR correction, like for your data, or what method to calculate the uncompensated resistance. So I'll briefly touch on those. So basically, for measuring the uncompensated resistance, let me pull up my little whiteboard here. So, for example, I want the thicker one. So, measuring IR drop, I'll just call it, right? You have the best option is usually EIS. There's also one called positive feedback. I should always use the text box, and I never remember until it's too late when I'm already scribbling words. So I hope this is legible. And the last one is current interrupt, which I generally don't like or recommend, but it is an option. So this is basically for measuring your uncompensated resistance. And then for applying IR compensation, there's generally two methods. It's very simply during or post after. Okay. This is the best method for determining it, and this is probably the best method for applying it, is to do it while you're running your experiment. So I showed you in my software where you'd plug in the value and do it that way. But it is possible to apply after the fact if, for example, you either can't with your particular potentiostat software combination, or you have the data already and you want to sort of correct for it afterwards. I can show you very briefly how to do that. So I think I have enough sample data here. I could sort of simulate here for you. Let me pull some data into an Excel sheet. I'll kind of demonstrate this very briefly, and I won't take too long, I promise, but I do want to kind of show you this. So, okay, so for example, let me share my Excel sheet. Okay, so this is some data from, you can see Levitch analysis from my RRDE webinar. So I've just pulled this data from one of those RRDE curves. So this is the potential, and this is the current. So if I make a plot of this, just so you can see what it looks like, okay. This is just like an LSV curve. I'm going to move the plot up here so you can see a little bit better. I like pasted it over a bunch of random data, so it's kind of a bit crazy. Let me make sure I'm sharing my screen properly. It appears I am. Okay, great. So here is it. So let's say I have this data already. This is a CV too. So same thing for bulk electrolysis. It would just be time versus whatever. But to correct for that ohmic drop, okay, so let's say my R is I'm going to make up something large just to, maybe it'll make the data crazy, but I want to kind of show a point here. Let's say I have like 300 ohms. Okay, so if you think of Ohm's law, V equals IR, right? Let me zoom in so I can kind of show these things here I'm doing. V equals IR. So basically this, if I multiply I times R, I get the ohmic drop. It's kind of like I was talking about before here. So what I want is E minus like E ohmic drop, which is I times R. So what I do is like, this is like the post IR correction, as I would take each point and subtract current times the whatever the uncompensated resistance is that I determined from EIS, hopefully. Okay. And I just drag this column all the way down through my data. And I get a whole nother corrected E column. Now it's pretty dramatic. As the current goes up, the correction becomes more dramatic. So if I add another trace, for example, okay, let me add another trace to this so we can see what it looks like in comparison. So this would be the next column over for this one here. So it's like this would be the IR corrected. Now it's a little crazy. I'm just making up these values, but you can see the effect. Like if I have almost no uncompensated resistance, then it basically coincides. If I have a huge amount of uncompensated resistance, this is obviously bananas. It kind of goes backwards. But the point is, that's post correction. That's how you do like a post correction. Now this is a CV, similar phenomenon. You're correcting the voltage, the potential, like the measured potential, let's just say, after the fact. If you're doing like a controlled, I guess controlled current experiment, you would correct the potential axis, the potentials with this IR correction. So that's one example of how you would correct this. Now that has problems associated with it. If you do, when you do that correction, it's a little complex. I'm not going to talk about this for too long. Basically, as it relates to cyclic voltammetry, one of the benefits to correcting during instead of after is that your waveform is more accurate. If you have a huge amount, which you don't always, but if you do have an appreciable amount of uncompensated resistance, if you don't correct until afterwards, you're fixing the data for the uncompensated resistance, but you actually have not corrected the waveform. Like for the CV, it's like go up and down at a constant rate. And what effectively is happening if you don't correct during and you have a really high amount of uncompensated resistance is that your waveform in reality for what is seen, I guess, by the electrode is actually more like instead of a straight up and down V, it'll be like wavier. And so it's basically the point is it's not a set scan rate, which is not ideal. And for a bulk electrolysis or a constant potential, constant current, something like that, it might have a similar warping effect as well. But in a quick way, that is how you can kind of afterwards correct for IR compensation. I hope that is helpful even in the absence of specifics, because again, I can't help you exactly with Gamry's interface and everything exactly. But that is a bit of a touch on IR compensation. I also think what I will do as I think about it now is my colleague Alex made a really nice video on IR comp. I'm just going to link that right now. These in my background here. So this is a IR compensation video. So this is a video on our YouTube channel. You're probably watching there now. Excuse me. So it's like 10 minutes or something like that. It's pretty nice and concise. And Alex basically goes into IR drop and IR compensation, how to get it, and all of that. So I do suggest that you take a look at that if you want some more information. Okay, Mohammed has a question. Let me see. Why sometimes during an electrochemical experiment our system shows overload detected? Yeah, this is an interesting thing, right? And again, it's sort of dependent on what potentiostat and software and everything you're using, because some have like a light on the front of the potentiostat that's like an overload light, and it'll turn on at various times. Um, I guess some might have an error that comes in the software or something like that. Everybody's sort of different, and I've worked with a lot of different potentiostats and softwares in my career, my experience. Um, so I can't give you specific advice per se, because first of all, I don't know exactly which system you're using, and then even if I did, I might know, but I might not exactly know what their um, error codes or systems mean, right? But generally, an overload like signal means that one of the ranges, usually potential or current, has reached its limit. Okay, so sometimes what that means is like potentiostats have multiple current ranges and sometimes multiple voltage or potential ranges. And so it's like if you're on, like for example, out one of our potentiostats has like current ranges every decade. So like 100 microamps, 1 milliamp, 10 milliamps, 100 milliamps, whatever. Okay. Let's say you're on the 1 milliamp current range and your current is rising and it's like 800, 900 microamps, 1000, 1 milliamp, and then it can't rise anymore and it'll flatline at that. That light would go on because it's saying, hey, this range is saturated. I've reached the limit or whatever. Sometimes it means that it's gone over the limit, which is either again potential or current. And sometimes it's an error. Sometimes it's a danger. It's for it's to alert you that there might be some danger, like you've reached beyond a limit. I don't know if some potentiostats have a light like this to indicate um, uh, that it's gone beyond a limit you put into the software. Like if you put, you know, um, I don't want to go above 4 volts or something, but it did. But it's like the potentiostat can go to 10 volts, but it's letting you know, hey, I'm over the limit that you told me to not go to. That could be the case. So you have an Autolab potentiostat. Okay, so yeah, I used Autolab. I used Autolab when I was in graduate school, but their software has since changed, and I don't know a lot about their new software exactly. But the other thing is that like you'll notice on some potentiostats that have the overload condition or light or whatever, is that it shows up like while the potentiostat's just loose hanging around doing nothing. And that's because it's like open. Like it's open. So I would say for Autolab, based on my memory, um, Autolab, the potentiostat used to have this odd behavior where like the cell would remain on, and again, I'm going from the past behavior, so I don't know if it still does this or if your specific model of Autolab does this, but if I ran my experiment, or one of my lab mates ran an experiment in the morning, right, and they did CVs, and it ended at 500 millivolts. If they didn't put like cell off condition in Nova as part of the experiment, even if they turned the like potentiostat off when they were done, when I turned it on, it was immediately applying 500 millivolts, like instantly. Like it didn't have a go to idle automatically condition. Now I don't know if that's still the case. I don't know if that's whatever, but my point is that what you might have happening is that it's applying a condition, like, and you don't know it is like, it shouldn't be. You think it's idle, but it isn't idle, and so it's trying to apply versus a reference it's not detecting, and so it goes to the rails. Like that could be an overload condition. Like if you don't have the reference connected properly, it will enter a feedback loop where it applies to the maximum potential that it can, and that hits an overload. But most of the time that happens because it's reached the limit of a range, again, like I said. So what I've just talked about in the last few things that I said, we're trying to estimate at some of the reasons why it might hit that range. But most often that overload means it's hit the capacity of a range, current or potential, of the instrument. And so how that exactly happens, of course, could be some of the things that I suggest. It could be anything else. Could be a lot of things, right? Electrochemistry is one of those trial and error kinds of sciences where you end up trying a million things and getting 1.5 million answers. But yeah, generally speaking, that's I guess let me just put it this way. The last thing I would say about this topic of overload conditions is that if you're running a regular experiment, like you're just trying to run a regular like CV, go back and forth, whatever, and you're getting an overload light during it, something might be wrong. Like you're going to want to check connections, check your again, if it's check your software, the parameters that you plugged in. Make sure everything's connected properly and your electrodes are in solution properly. Especially if, I mean, right. I guess I should say, if you're getting poor data and you're getting an overload, like it's hitting a limit, something's not connected, something's not wet, right? Like there's something really wrong going on. You want to stop running your experiment and troubleshoot. If you're getting good data, like the data looks fine, but the overload light is coming on, I don't know what is going on. that like, if that's the case, something very bizarre is happening, or it might be an error, like maybe the instrument's malfunctioning and giving you an overload condition incorrectly. Especially if your data looks good, it might be, I don't know if you would call it a glitch, but something odd is certainly happening. That in that case, if you're getting like decent data, but the overload light still, or overload error message or something keeps coming up, you would probably need to contact the potentiostat manufacturer. All the other stuff I discussed is probably within your ability to troubleshoot and figure out why things are going wrong, I suppose. AJ has another question here. I performed impedance and it has observed that the sample, which also allows electrons and protons transfer, so this is with the membrane discussion from before, showed low resistance via impedance and high current via DC potentiostatic mode. Well, that tracks. Fresh sample allowed very low current via DC and high resistance via, yeah, well, that couples together well. I mean, I don't know if you have a specific question about that, but right, if you have low impedance, it's going to lead to high current. That's just Ohm's law, right? Low impedance means more current travels through it, and a fresh sample shows very low. I mean, honestly, like this is a interesting phenomenon and an interesting topic, but fundamentally, a fresh sample, um, I should say again, it's sort of fundamentally here, a membrane allowing any current to pass directly through it is probably a terrible membrane. Like quite literally, the diagram I described where the membrane and you have anode and cathode on either side, it's actually not even that, like for Nafion, for a PEM fuel cell, it's actually more than that. Like you quite often, quite literally paint or spray or something your anode and cathode on the membrane itself on either side, and electrons don't go through the membrane. Only protons. So, like Nafion is tremendously electrically insulating and tremendously ionically conducting. It's really great. That's why it's used in basically all PEM fuel cells. So, um, you know, this is an interesting phenomenon. You know, some degradation process is creating some electroactive pathways, or right, some means for which electrons can travel through. A membrane should have basically infinity electrical impedance, right? I mean, it should have no DC current possible for it to work. So this is an interesting, I guess this membrane must have some attractive qualities or parameters for you to be looking at it and using it, of course. At least I would assume. Otherwise, there wouldn't really be any purpose in studying it. But in a vacuum, I would say it's odd to consider wanting to use a membrane that allows direct electron transfer. It's just antithetical to what a membrane purpose is in a separated system like a battery or a fuel cell. Race Bannon is back. Nice to see you again, Race. So did you ever use GEIS, or galvanostatic impedance, AA, adaptive amplitude technique? It seems this technique is better than GEIS or PEIS. Adaptive amplitude. I'm not familiar with this. So the answer is no. EIS, adaptive amplitude. I'm going to look. See, I don't know. Were you the one last week, Race, that asked about the DC EIS, which I also hadn't heard of and thought was a joke? It's a strange phenomenon here. EIS-AA, adaptive amplitude. So I guess that would be some sort of system where the potentiostat monitors like automatically what the impedance is or something, and adjusts the amplitude accordingly. Is that accurate? Let's see. See if I can find some adaptive measurement. Yeah, it's. I mean, in the absence of more information, it strikes me that yeah. So you're constantly coming back and asking me about strange impedance things. Here's what I would say. So if my interpretation is correct, which I mean the terminology seems to indicate, that would be like the system automatically attenuates or grows, whatever you want, whatever it is, the amplitude of the sinusoidal pulses as it goes along. Okay. If the system can do that, that will almost certainly be the best way to do it. Almost certainly. Unlike again, I'm not sure if it was you or it was someone else, but there was a question in one of the weeks, one of these live streams. Again, I can't remember. They kind of blend together. I've done this every week for months now. But someone asked about like there's all sorts of terms I had never heard of. It was like PRB, PBRS, PRBS, pseudo random, PR, pseudo random binary sequence. And that was something like a waveform that was kind of like it grows and then it got smaller or whatever. So some odd sinusoidal, you know, waveform as a means to get like state of health data. Anyway, my point was that it sounds interesting and maybe you can get some cool data from it, but it's not really impedance, right? Because it fundamentally violates the rules of impedance. It's like it's not steady state. It's maybe not linear. It's changing or whatever. Now, one of the hallmarks and rules, if you will, of impedance data fundamentally is that the result is independent of amplitude. Okay. So I talk about this in my webinars, for example, but impedance is fundamentally this experiment where you're trying to optimize the amplitude, right? You're trying to get big enough to perturb the system, but not so big it's not linear. Which means if it's too small, it won't perturb the system. But if it's too big, it's all kinds of crazy stuff is happening. And so ultimately, if your system is super well behaved, linear, and not a problem, if you do 5 millivolt amplitude and you get a spectrum, and then you do 10 millivolt amplitude, you should get the same spectrum if it's about the same. So what that means in theory is that you could do half 5 and half 10, and you get the same spectrum. You could alternate 5 and 10, 5 and 10, and you get the same thing. So again, what that suggests to me is that if you can adapt the amplitude of your impedance signal as you progress through the frequencies to make sure you're always at that sweet spot of optimization, that would be perfect, because there are some systems where especially those where the impedance changes dramatically over the frequencies that you are doing. Let's say you're doing a really wide range of frequencies, right? As the impedance usually goes up, as you drop your frequency, it makes it's like you might need only a very small amplitude at high frequency because your impedance is low, but you might need a much bigger amplitude at low frequency because your impedance is high, which means that your current response is really low. So it's like, if there's a system that can adapt the amplitude as it goes, it would not, in theory, violate the rules of impedance, and your data would probably be better at all frequencies. So, again, as a summary here, no, I haven't used it, and yes, it does also seem to me like it's way better than both. Whether it's galvanostatic or potentiostatic probably doesn't matter to me, at least anyway. Sometimes galvanostatic is a nicer way to control things, but it really actually depends. Like if you have a low impedance system, probably galvanostatic is better. If you have a high impedance system, probably potentiostatic is better. But either way, if you have some kind of adaptive amplitude method, that sounds really cool. I would say probably you should go for that, or try it anyway. But the downside, if there is one, would be that you're trusting the instrument or the software algorithm to do that optimization for you. And it's of course possible that it's wrong or it doesn't do the best job. So it could backfire, I suppose you could think, if it did a poor job of getting your amplitude optimized at some frequency range. Maybe it's not perfect like any computer algorithm could be. So that would be the hesitation, I suppose you could say. Let's see here. Indra has asked if I am a physicist. I am not a physicist. I know a little bit about physics, but I am a chemical engineer by trade, or by school, I guess, and electrochemist specifically by training. So I went to school for chemical engineering, and so most of my colleagues and most of the people, as I learned throughout my career, who do electrochemistry are in the chemistry departments, which probably seems obvious to you if you're watching this and you're in graduate school or a postdoc, and you do electrochemistry. is that you're in the chemistry department. I got to graduate school and ended up in a group uh, doing electrochemistry and PEM PEM fuel cells and alkaline fuel cells, and then eventually some lithium ion battery stuff. And I was in the chemical engineering department. I went to, did my undergrad in chemical engineering, and it's like slightly different kinds of stuff. Like you design plants and you do like different sorts of analyses. It's kind of a different world, actually, kind of interestingly, at least to me anyway, because I mean, I had some I don't know, chemistry classes or things like that, but the engineering curriculum is a little fundamentally different. And it's sort of like you don't always know what you don't know, right? Like until you're exposed to it, I guess. And so I got to graduate school and chemical engineering department, and okay, great, this professor's doing electrochemistry, and I joined the group. I liked it. It's cool, great. And then I start, my job here at Pine many years ago, and I'm all my colleagues and everything, and then, meeting professors and everything. And it's like, everybody's in the chemistry department. Oh, you're in the chemistry department too. And then all my colleagues and my boss and everybody, all of us who are electrochemists, I'm like, wait, did did you guys get degrees in chemistry? And they're looking at me like I have 7 heads. Like, yeah. And I'm like, oh, I didn't. Should I? Am I fired? Like, like it was not expected, I guess. I don't know. It was a funny culture shock for me, in a sense, realizing that most electrochemists are actually, in fact, in chemistry department and not chemical engineering. So it's kind of funny. I almost feel like a unicorn. Um, I not realizing that, at least it seems to me, that the vast majority of electrochemists are in chemistry departments in various universities, and not in the chemical engineering departments. So anyway, that's my little short diversion there. Race has asked why ACIR usually done at 1 kilohertz. Do you mean to get the uncompensated resistance? I guess, is that what that means, right? AC, alternating current, IR compensation. I assume that's what you're doing. I guess it's not always done at 1 kilohertz. But that is probably a common frequency at which people measure it. And the reason is that you are usually calculating the uncompensated resistance at high frequency. Because at high frequency, you're bypassing most of the capacitive effects. And so you're isolating resistive effects. Resistors have an impedance that's independent of frequency, whereas capacitors have an inverse relationship between frequency and impedance. So at high frequency, capacitance goes down. And so if you want to isolate purely resistive effects, which at the highest frequencies is mainly a result of uncompensated resistance, solution resistance, those kinds of things, you pick a high frequency. Now, the reason why 1 kilohertz and not 1 megahertz, and again, it's not always 1 kilohertz, sometimes it's 10 kilohertz, sometimes it's 100 kilohertz, it's not always specific. It can depend on the system, depend on, on your experimental setup and everything. But the frequencies that are the highest often are coupled with things like artifacts. Reference electrode artifacts, and I've talked about this in previous weeks, where it's like stray capacitance from the glassware, the fill solution, some of these phenomena. But basically, at the highest frequencies, it's like you start probing other odd stuff, like those stuff, and so you don't want to get misled into the impedance being uncompensated resistance, let's say, when you're actually probing like artifact effects that are secondary to your actual system. So it's like you want to go slightly lower than the highest frequency, but much higher than where all of your like Faradaic capacitive charge transfer processes start occurring. And so that's why 1 kilohertz, usually in the just something between 1 and 100 kilohertz is usually where you end up. And practically, um, what some software programs do is they take a few pulses at some frequency. Sometimes you pick the frequency, so you type in 1 kilohertz, or sometimes they'll find it automatically. There's some algorithms. Sometimes it'll take a short range, like between 100 kilohertz and 1 kilohertz, and do like a bunch of points. And what the software will basically do is find the most resistive points in those frequency ranges. So it's try to find that sweet spot, like I mentioned, where it's below frequency where there's uh, artifacts and things from the reference electrode or the cabling or whatever, but it's above all the other stuff. So basically, that point usually ends up being where the phase angle is closest to zero. And 1 kilohertz, for a lot of especially aqueous systems, happens to, for whatever reason, be close to that point. So like if you look at the phase angle diagram on a Bode plot, for example, you'll see it do weird stuff at high frequency, and then sometimes it'll get close to zero, and then it'll dip for whatever processes you're studying. But wherever the phase angle is closest to zero is fundamentally the most resistive, because the phase angle, another way to think about the phase angle of impedance data is that it is kind of the degree of capacitiveness being observed. 0 degrees phase angle means there's no phase lag, means it's purely resistive at that frequency. Whereas minus 90 degree phase lag means it's purely capacitive. And so anything in between 0 and minus 90 are different degrees of capacitive. And so you're trying to find the high frequency point where the phase angle is closest to 0. And the corresponding impedance magnitude is roughly equivalent to the IR drop, the uncompensated resistance at that point. Andrew Rodriguez asks a very important question. Does this channel have social media so I can follow? Of course we do. So we have all of the things, and this is not my area of expertise. Let me pull up a thing here where I can sort of dump some of those information and links for you. I think I have it. Like we have Twitter and Facebook and LinkedIn and all of these things, and I am not good. Let's see. I will find it for you and put a link to those various ones. But we do have that. So obviously, if you're asking this question, you are on YouTube, and so that's the one of our social channels, if you will. Of course, YouTube is more for videos and these kinds of content here, so you're not going to get. It's a different sort of an environment here. I want to find. I have kind of a list, which I think I can find. Not there, but I will find it for you and post links to our various social media locations. But you can also search for us in the meantime while I foolishly search through various records here to try to find it. You can certainly, here it is, Twitter, YouTube, LinkedIn. I think these should be links to some various platforms of us. So I guess it's called X now, but there you go. So there's some links in the chat for you. Sorry, it took a minute. But yeah, we're in all the usual places. So it's either Pine Research or Pine_Research or something like that. My much more qualified and capable colleagues who are much more much better at at social media than I am. I'm kind of a dinosaur in this respect. I don't really do social media very much personally. In any case, please check us out. Of course, YouTube is where we're the most active for sure. Alex and I do this live stream all the time. As I said at the top, our podcast is coming up in about a couple months. It'll be available on YouTube, and this is where we do most of our current content, I would say. So YouTube is a good place where we're actually pretty active. Especially talking with us live here. So, and I'll plug again as we have. I didn't mention this at the top, but we have if you're a member of our YouTube channel, you can join us on any of these live streams on Fridays live. You can join us in this platform we're using called Restream. You can see it at the top of the screen here. And you can join me and talk live. So yeah, the format here is you type your questions and then we answer them and we try to draw some stuff. But if you had, for example, some data you wanted to share and ask our opinion, or you wanted me to try to do some fitting or just more interactive, right, in the community section of our YouTube channel. If you're a tier 2 member, you can see a post with a link to this exact event that I'm on right now, and you should be able to join. And then I could let you in or kick you out or whatever I need to do, and you can talk with me and we can chat and you can ask questions. So that is sort of an open invitation for YouTube members to join us on these live streams. So we've had a couple people do that in the past, and it was kind of neat to talk with some of our viewers. So we're trying to make that as a resource to you if you want. Race has another question. Could you please dig into the reference electrode chemistry? Why does it have a glass frit, small pore? I've seen people using only AgCl wire as the reference. Thanks. Yeah. So, let's see here. Alex is certainly better at some aspect of this, but I'm going to try to answer your question for you. Alex is always better with drawing the potentiostat diagram. He did our video. He did a video on that on the website where he, what's a potentiostat and how it works and everything like that. So I'll try to focus on it, maybe not quite so much from how does a potentiostat work and why is reference electrode needed in that respect, but I'll try to answer your question about why that's the case. Now, the first answer to your question, the reference electrochemistry, digging into that, the answer is the Nernst equation. Okay, so the Nernst equation is basically the reason, or it explains what a reference electrode, why it has a potential where it does or whatever. So I always look it up just to make sure I don't write it down stupidly. Just try to get the right terminology. But right, so E is equal to, I talked earlier about overpotential. So E naught or E0, whatever, is either in the top or the bottom. Was it minus RT over NF? Yeah, minus RT over NF times the natural log of, usually it's called Q, which is the quotient. All right. So reference electrode chemistry basically follows the Nernst equation. Okay. So for something like AgCl, you have the reaction Ag plus, hang on, let me, I want to make sure I don't butcher these equations. I know this is kind of fundamental here, but yeah, I mean, very simply, it's this goes to AgCl, but it's two half reactions, right? Let me see here. I'm trying to figure out the right way to look at this. Yeah, probably, but yeah, probably better to, usually you draw it as a reduction though. So yeah, I'm gonna draw it this way. Okay, so as it relates to the Nernst equation, AgCl as a solid plus an electron is either in equilibrium or goes to Ag plus Cl minus. And so these are like aqueous ions. Okay. So this expression right here, should put a solid here. So this is like the reduction reaction. Okay. And this has a particular potential associated with it, right? This is an E0, what, it's 200 something, minus 200 something. Again, what is it? 222, I guess. Yeah, it depends where you look, but let's just call it 220 millivolts. Sorry if you can't see that. I'm off the screen a little bit. Oh, you can still see it. Okay, great. Okay, so basically the Nernst equation, this is the thermodynamics of this, right? Of this reaction. So when you have a silver wire in contact with silver chloride, this reaction is thermodynamically what is dictating its potential. And then the reaction quotient, so Q is really technically the concentration of the reactants over the products. So in this case, it's Ag, and I'll show you where these go away briefly here. Concentration of Ag, that's a product raised to the power of its moles, but it's 1. So these are all exponents up here, assumed 1, to the concentration of chloride to the 1 over the concentration of AgCl. And this is a solid to the 1. That's technically Q. Now these go away because sort of the rules of chemistry here, right? That solids are not included in the quotient diagram or whatever. So basically, effectively, you have this corrective factor here. Okay, so RT over NF, N is 1. RT over F, R is 8.314. Whoops, I was just going to get that number for you. 8.314, temperature 300 over 96485. So that's 0.025. 0.025 times ln of basically the chloride concentration. Okay. So here's the point. Basically, why do people use a tube with a frit and all that stuff? I promise I was going somewhere with this, which is what you're questioning. Okay. This potential here is impacted by the chloride concentration, right? If my silver chloride wire was just determined by this E0, by the potential, that would be great. But the actual potential we measure is dictated by the Nernst equation. And so it is 200 whatever, but it's also impacted by this term. And so that requires, if you want a stable condition, for you to have a set chloride concentration. Because if the chloride concentration is changing or non-existent, you have an uncertain situation. And of course, the goal of a reference electrode is to be as stable, unchanging as a point as possible for the potentiostat, for your results to not be drifting or moving around. Now, the situations where people might use the AgCl wire only are ones where they probably have chloride. So like if you're doing a brine solution or KCl or whatever, you can just dip your silver wire with silver chloride in, and assuming you're not changing the concentration over time or diluting your solution or something crazy, whatever the chloride concentration is in solution will lock this potential in place pretty nicely. But people don't always test with chloride. Sometimes you're doing different salts and stuff like that. Okay. And so the reason for the glass tube and the frit is mainly to have a set chloride concentration and to keep it that way, isolate it. Because if you have an open tube, that will all flow out, and then you don't have a set chloride concentration. So you have to have a sort of a contained thing. Okay. Now the other reason for the frit is that you want to have a contained thing. So you could say, well, why don't I just put it in its separate tube? Well, um, the potential that's an answer that is related to the way a potentiostat operates, right? So if you have a if you let me explain it this way: the reference electrode, that silver wire, has to be able to communicate, quote unquote, in solution with the working electrode one way or another, because the potentiostat is measuring the potential between the working and the reference electrode, and it's using that to it's setting everything with respect to those two. Well, those two can't have a potential between them if they're not connected. They're not physically connected. They have to be physically connected somehow. And so the only way we do that is just like we connect everything in electrochemistry is through electrolyte, salt. Right? It's the same reason that electrochemistry doesn't really work in perfectly deionized water. Can't. I mean, the impedance is infinite, and there's no circuit connected. Okay, so you have to have some communication, which is through the movement of ions. So your frit serves two purposes. It has very small pores that prevents fast or like large amounts of diffusion. And part of the reason is that you don't always want chloride ions interfering with your active electrolyte. Sometimes chloride can be bad for a couple of reasons. But it does allow some movement of ions. It has to. Because if it doesn't, there's no communication, like I said, between the working and the reference. Okay, so some ions have to be able to move, which is the passage of charge. And there's like a train of ions between the AgCl wire and where your working electrode is, and they have to go through the frit. They have to go somewhere. And so that is actually another thought process of this is about, as it relates to the artifact issue I talked about before. That's when the potentiostat and the reference is trying to communicate directly through the glass wall as though the frit isn't there. And that's when you get an artifact, because there's no communication that way. It's like a very poor capacitor, but there's no direct communication. There's no ion movement through glass. It's solid glass, right? It doesn't. So if you had a pure glass body with no frit, you would have this capacitive effect trying to make communication between the inside and outside, but it wouldn't work, especially at low frequencies. When that capacitance starts getting really, really large, you would have no communication. So the frit small pores are to isolate as much as you physically can the chloride solution so that you lock that Nernst equation potential for your reference electrode in, and prevent a lot of chloride from leaking out and getting into your solution or whatever, but also still allowing some ionic movement and communication so that you actually have a completed circuit. So you actually have a way to sense the potential between the working and the reference electrode at all. Because if you don't, there is no potential there and it won't work. You might as well not have a reference at all. Or you just put it in directly into your solution, which, like you said, does happen. And it can work if you have some chloride in solution. And I have heard people who have used an AgCl wire, like an AgCl wire, not in chloride solution, and it works okay. I think that the issue with that can sometimes be that it won't work like indefinitely, because there is still a potential there, right? Like there's still a potential associated with AgCl, like I drew. But and to some degree, I think that like stray chloride will locally dissolve like in solution right near the wire. And so that creates some, like, satisfies the Nernst equation in some sense, where like if there's a very small amount of local Cl minus concentration right near the silver wire at all times, you sort of lock that potential in. But it's an unknown. It's less ideal because it's like At least if you have an AgCl and 4 molar KCl, like you know what its set potential should be, right? And that allows you to reference everything for comparing to literature, for adjusting to NHE or SHE, or adjusting to any other potential, comparing it with your previous results, etc. That's one of those things about the reference electrodes that's frustrating, but also necessary, because you are trying to get yourself a known point. Now that point can be tricky or not work or not be what you thought it was in some situations. And there's like 1,000 reasons why. And reference electrodes don't always work. And there's, if an experiment is going haywire in electrochemistry, it's like 80% of the time it's the reference electrode. It's always the reference electrode. We have a joke here at Pine where it's like, if someone is having a problem, it's like, it's the reference electrode. Like, it's almost always the reference electrode. It's just it so often is the reason why people have odd data, or something doesn't behave the way it should, or what have you. The reference electrode's almost always the culprit. And but the benefit of it is that, at least in theory, right, is that when you're reading someone's paper and someone's dissertation, and you're looking at their data for their oxygen reduction or their oxygen evolution, or whatever you're looking at, it's like the benefit is that you can compare your results with theirs, because they converted everything to the hydrogen electrode, or they reported it versus AgCl or calomel, and you're doing your experiment 50 years later in a different setup, and you can still make a direct comparison to the potentials they did, because they compared it to a thermodynamically based, like, solid reference. That's what a reference potential is for. So it's a really strong argument for why reference electrodes are still needed. And I have this running, like, professional pursuit that I keep trying to think of ways that we can avoid using reference electrodes forever, because they're such a pain, and they cause so much headache in electrochemistry. And or just avoid using frits altogether, or whatever. It's like, I've always felt like there's got to be some, like, practical electrical way that we can, like, design an electrochemistry experiment where we don't have to use a reference electrode. And I'm not talking about 2 electrode systems. Like, obviously you can avoid using a reference electrode if you just do a 2 electrode system. But that has its own problems, because then you have a unstable reference point, or what have you. But yeah, if there was a way to avoid having to use a reference electrode at all, or having to have that frit that adds that impedance, and makes things start to behave poorly, that would be a really big benefit to the community. And well, let's just say that obviously I have not been successful, and I probably never will be successful, because it's just not it's not really physically possible. Hey, Chris, you're otherwise occupied today, but wanted to drop in and say hello. So yeah, no worries. Good to see you again. Chris is one of our resident live stream attendees, always helping out with questions every week. So it's good to see you again, Chris. Let's see, one more question on the reference electrode. On which factors do we choose a reference electrode, based on aqueous, non-aqueous, or ionic liquid electrolytes? For which system could we use lithium metal as a reference? So for aqueous electrolytes, pretty often the criteria for choosing the reference electrode is matching the anion. That tends to be a lot of what it is, and it's a lot of times based on, fundamentally, because that frit blocks a lot of the transport, but it doesn't block all of it, right? So, um, so if you accept the premise that over, longer times usually, but over some period of time, something in your reference electrode fill solution could make its way to um, your main solution, then it would be preferable if that thing, that ion, was something already there. Okay, uh, so for example, when people are working with sulfuric acid, they tend to use mercury sulfate reference electrode. So the mercury sulfate reference electrode couple, you'll see that a lot in ORR papers, because ORR, people usually do half molar, 10th molar, whatever, 1 molar sulfuric acid, H2SO4, and the excuse me, the mercury sulfate reference couple has a potential of about 650 millivolts, and it has usually a supporting electrolyte of K2SO4. So great. So it's like maybe some potassium leaks in or whatever. That's not going to do very much. It's pretty inert. But if any of the anion works its way in, well, you have sulfuric acid, which already has sulfate, and you have sulfate in your reference electrode. So it kind of makes sense, right? And it would, in theory, reduce the sort of diffusional driving force, because you have the same ion on both sides. The concentration is different probably at either side of the frit, but the same anion kind of makes sense. On the other hand, and again, conversely, some people prefer to avoid using something like calomel, which is mercury chloride, or AgCl for those systems, because the chloride ion is not the same. Yeah, osmosis could be an issue on that. Yeah, you can have the diffusion of water in either direction, diluting one or the other. Yeah, of course, Chris is correct in that. And then the other reason, of course, is that chloride sometimes is a problem for, in particular, like platinum-based electrocatalysts. Chloride has been shown to like adhere to electroactive sites and block them, and that's obviously not ideal if you're trying to use your electroactive site to do oxygen reduction or whatever. So people will avoid sometimes using chloride, or they'll use something like a salt bridge to separate the reference electrode, because for the second reason that people choose a reference electrode is based on how good its chemistry is. So I talked about the Nernst equation, and that sets it and everything. But there are just other little things, like, for example, the mercury sulfate is used a lot for sulfuric acid. The problem is the mercury sulfate reference couple is not as good. It's like it's a little less stable. Mercury sulfate is a little more soluble, so it's like it could go away slowly over time. I don't know how bad that problem is really fundamentally, but people have there's sort of a general I don't know, you call it a consensus, or just sort of a general knowledge from experienced electrochemists, that the mercury sulfate reference couple is like a little less stable than, for example, calomel. Like, again, this is just sort of my sort of, I don't know, tribal knowledge, experience, what have you, from electrochemistry career, is that in my estimation, the most stable reference couple is calomel. It's really great. Um, it but it has chloride, so it's like if you're trying to avoid chloride, you're like, well, do I, you just have to pick. But sometimes people pick calomel just simply because it's rock solid. It's really great. Standard set, good stable potential. It's not really affected by anything else. So if you can tolerate a little chloride, or you can use a salt bridge or something, calomel is usually a really good choice. And then, for example, alkaline systems can be more intolerant for glass and other chemicals. So people use mercury oxide. You can still use calomel as well in some situations. Depends how strong your alkaline system is, stuff like that. So those are a couple of the considerations for basically all the aqueous reference electrodes, I guess. As far as non-aqueous or ionic liquid, which is redundant because ionic liquid is non-aqueous. That's where you get into the realm of pseudo reference or other kinds of couples. So for example, you just use a silver wire or a stainless steel or just platinum, which is something like a relatively non-polarizable metal, which has a pretty stable potential, but it can move and drift. It's not Nernstian in the way. Sometimes people will do stuff like in acetonitrile, you can make like a silver nitrate with like whatever the nitrate equivalent is of a non-aqueous dissolvable salt, right? You can get some nitrate. I'm not the best with like non-aqueous salts. I'm not. I know like TBA-PF6, right, is like the supporting electrolyte. I don't know if they make like it's like TBA nitrate a thing. Anyway, you can make various couples. So they're not always as good. Sometimes what people do is they roughen up a silver metal, and it makes an oxide layer on it, or you oxidize it and make an oxide layer. So like AgO can work kind of as a reference couple for non-aqueous electrolyte. It's not, again, none of these are like as good as like a calomel and aqueous and those kinds of things. And then to your last point, can you use lithium metal as a reference? Yeah, you can for sure. Lithium, that's like battery testing is, usually 2-electrode. And so if you're testing the cathode or the anode, a lot of times you'll use lithium metal as the cathode or the anode, because lithium can act as a lithium source or which is like the cathode, or the lithium depositing electrode, which is the anode. Basically, lithium metal can serve either purpose, right? I mean, in theory, a lithium metal was the perfect cathode for a battery, but it doesn't work. This is why we have NMC and other stuff. I'm sort of diverging a little here into battery talk, but the point is that when you're doing this and you're using lithium metal as the anode or the cathode, for example, it is also the reference, right? Because it's versus Li plus, and that has a voltage of like 3 volts or whatever. So that's also why a lot of thermodynamically, fundamentally, the minimum potential, the minimum voltage for a battery is like 3 volts, because that's the potential of like the lithium couple itself. So yes, you can use lithium as a reference in non-aqueous systems, and that's actually pretty commonly done. Even in a situation which I never did personally, but it's a little cumbersome a lot of times. If you're doing batteries, sometimes people will jam a reference electrode into the battery and turn a 2-electrode into a 3-electrode system. And I think sometimes they just shove a piece of lithium metal in it, and they do it that way. And the lithium metal works as a reference for both the anode and the cathode. So you can sort of study the voltage of each of them separately. Because, you're looking at the voltage of a battery, it's like, oh, it's 4 volts. That's relative, which tells you how much energy it has to deliver, but it doesn't tell you what the individual voltage of the anode and the cathode are. Because like you could have 4 volts. Well, does that mean that they're both equally okay? Or does that mean that the anode has a terrible voltage, but the cathode has a great voltage? And so it's like one of them is degrading faster than the other, something like that. So using lithium metal, for example, in that case as a reference allows you to get the independent potentials of each anode and cathode in your battery, which can be useful for diagnostics. Chris is getting ready to get the insulation sucked out of the attic this weekend, fix a bunch of ducting and wiring. I did some wiring like once. It's really fun, but it's also really nerve-wracking. I feel like as an electrochemist and someone who works with amps and volts and stuff like that all the time, I have a very odd fear of like electrical work. It kind of fascinates me, but like also wire, it's very different to do an impedance diagram and like, show a resistor and a capacitor and inductor and do some EIS circuit fitting, and then to actually run wires through conduit in your shed or your house or whatever, and do, make sure it's working, and you flip the switches and it works and everything. It's a whole different animal. And it always kind of freaked me out. Even now, it's like we have electrical engineers at my company, obviously, and we develop instruments and we do all that kind of good stuff. And and it's like I'm always like fascinated when our like electrical engineers, if we're talking about something or they're showing me stuff, and they'll like they're working on a potentiostat or they're working on a cell or a setup or whatever, and like, oh, adjust the voltage of this thing and like grab the electrode and just take it out and touch it or whatever. I'm like, but it has current going through it. Why would you touch it? It's like, milliamps or like microamps. Like you can't even feel it. I'm like, I don't want to touch it. Like, what if it's that? Because like an amp, I think like isn't the typically like an amp can kill you, right? Like generally speaking, the magnitude of current that will cause severe like injury is like about an amp or something like that. And so I'm always just freaked out by like, why would you touch anything that has current going through it? Like it just it's like I don't like freaks me out, even though I'm an electrochemist and I should be like more aware of these things. Somehow it always freaks me out here. I should go check out large scale electroplating plant, taste of the applied electrochem. Yeah, actually, a friend of mine back from undergraduate, he did some studies, some graduate work with electroplating, and I guess with like either the like computer chips and chip industries or whatever, copper refining. Yeah, mega amps. Good lord. Yeah, that freaks me out. It really does. It just freaks me out. Like that's so much current. Oh my gosh. But I know that whole there's a whole industry of plating, copper plating with semiconductors and stuff like that. Basically, it's like there's a whole industry of filling pores with copper electrochemically, like electroplating stuff. And it's a whole game of you have to suppress the speed at which it plates, and then sometimes you have to accelerate it because if it fills too quickly, it'll have a hole, like it'll fill incomplete or whatever, and the pore will have a hole in it. But if it fills too slowly, it's too dense or something like that. So it's like you have accelerants and decelerants, and so there's this whole field of that or whatever. And yeah, copper refining, aluminum production, all these kinds of fields are fascinating. It's I think that I think that a lot of times as electrochemists, to me anyway, maybe not so much for me because I know like batteries and fuel cells and stuff are like really major, and well, solar cells too are real world applications of electrochemistry. But sometimes they feel more like, well, still theoretical in a lot of ways. I guess batteries are everywhere, but like um you know the production of these metals, copper refining, all those kinds of, I mean, that's like huge business and huge industry. So yeah, I don't know. It's kind of refreshing to think about some of those industries um, that are also part of electrochemistry. It's bigger than I think about sometimes. Brighteners and retarders. I don't. That might, if you remember correctly. I mean, I haven't heard that terminology. Retarders or decelerants or suppressants. One of those, any or some of those terms are used, I think, interchangeably to like slow down the process, right? And brighteners or accelerants, something like that. Anyway, yeah, different chemicals they can use to kind of speed up or slow down the process so that um, you fill a pore, you electroplate at the right rate, and all that kind of stuff. Let's see. Ray says, I can understand with respect to anode carbon material. How does lithium as reference in a 3-electrode setup help to study a cathode material, lithium oxide? Um, so okay, so if you're thinking about a 3-electrode system, a typical 3-electrode system has a working encounter and a reference, right? Um, your potential is with respect to the reference, and you're getting the potential at the working electrode. You don't know what the potential is of the counter electrode. but it has a potential. You're just not usually measuring it. Okay. So one way to think about this with respect to a lithium ion battery is that if you have a reference, it can be used as the reference for either side. Like there's nothing that precludes you from using it as either side. Basically, it's just a matter of like if you were to connect the working electrode to either the anode or the cathode, like the working electrode lead of your potentiostat or your battery cycler, right? Because then whatever the working electrode is connected to will have its potential measured with respect to the reference, which in your case is like a lithium metal. So there's no difference between what its potential is. This I shouldn't say that. It's not what difference. It, the measurement that you do um, will be with respect to whichever one is the working electrode, basically. And then there's other situations where you can simultaneously measure the potential of both working and counter, anode and cathode, whatever, um, with respect to the reference. And in fact, your questions almost feels backwards to me because actually, when you're making a full battery with a like lithium oxide or lithium NMC, cobalt oxide, lithium iron phosphate, whatever, and carbon, let's say, as your anode, you actually normally connect the working electrode if you're doing like a potentiostat connection to the cathode, not the anode. And so actually fundamentally, you're probably, if you're doing a 3 electrode measurement, you'll be measuring the potential of the cathode, not even the anode. But there are ways to also use that same reference to measure the potential of both or either of them. Because again, it's like if you have a 2 electrode system, you're just getting the voltage difference between the two, wherever they happen to be at. Um, and you can have the same reactions occurring, charge, discharge, whatever, at the both of these anode and cathodes while measuring their potentials independently against, and that's just kind of a potentiostat operation clarification, I guess I'd say. Like it's potentiostats, like a bipotentiostat can do this. For example, you can use one working electrode to measure the potential of the anode and the other one to measure the potential of the cathode, for example. That's just kind of how you can do, for example, with a bipotentiostat. But it's really just, I mean, the answer to your question, I guess, in the most basic sense, is just circuitry / connection configuration with your potentiostat. You know, and the potentials you get will be different because pure lithium metal might have a similar potential to the cathode, so your potential's different. Because remember that it's just like a fuel cell or like anything. The E cell or whatever is basically the E cathode minus E anode. So they each have individual potentials themselves, and you subtract them and you get the cell potential, basically. So yeah. So I hope that's clear. And if you kind of had a different idea about what how you're asking about this question, go ahead and type it in here. Arya asks, what is the application of single frequency impedance? A lot of times it can be used empirically to track state of health. Sometimes you can use single frequency to track the change in the uncompensated resistance, for example. We talked earlier in this live stream about like people tend to use like 1 kilohertz or 10 kilohertz as a estimate frequency where you're mostly resistive. And so that impedance is relatively well correlated with the uncompensated resistance or the IR drop. And so you might periodically take one frequency, like 10 kilohertz impedance, only one frequency, to see how the impedance of that uncompensated resistance changes over time or with whatever variable you're changing. So that's one reason. The other is, as I said, like an empirical thing. Sometimes certain parameters like the impedance magnitude or the imaginary impedance or the phase angle or some parameter can be empirically correlated to things like temperature or depth of discharge or something like that. So uh, sometimes that is a way people will use the single frequency diagnostic kind of thing to track empirical relationships, get a sort of instantaneous, and the benefit is, of course, it's quick. So it's like you don't have to do a full EIS spectrum. You don't have to go to really low frequencies. Can take a while and all that, right? So you do a single frequency to get a sort of quick snapshot of the state of health, of the state of charge, or something like that. Those are some of the applications of single frequency impedance. Chris says the brightener selectivity removes peaks in the system by attacking the points of highest current density, helping to level the surface. Yeah. Brightener. Yeah, that term I haven't really heard in this respect. Again, I've seen it more as accelerant, decelerant, suppressant, suppressor, so something like that. So some of those terms are probably interchangeable, or maybe they're used in different plating applications. Maybe it depends, right? It might be copper on platinum, or copper on semiconductors, or things like that. You have different formulations or different additives that affect that process in different ways. Anyway, that's kind of an interesting process. I do always like to keep aware, I guess. Oh yeah, the other one I was gonna say was like glucose testing, sure, like for like diabetes testing, right? Batteries, fuel cells, stuff like that. I always like to keep sort of a, I don't know, knowledge, just running on the edge of my mind of like what electrochemistry is useful for, because it like justifies our existence in some sense. It's like, why do we keep studying electrochemistry? I think last week someone asked, like, is electrochemistry saturated? And it's like, gosh, I hope not. But even then, it's like, whether the topics are saturated is one question, but then whether the research in each of those topics is in itself saturated is like another question. Let's see. Race has clarified the question about the lithium reference. Put the question in a different manner. Could we study lithium-ion battery cathode using lithium as the reference in a 2-electrode set? Yeah, you can. You're thinking in terms of intercalation, yeah, since carbon graphite is used to store and release lithium ions. Yeah. So actually, I think I might have sort of hinted at that, or said that maybe in passing. Maybe I didn't clarify it well enough. That is very commonly what you do when you're studying either the anode or the cathode, is you use lithium metal as the other one. So if you're studying just, and I did this when I was in graduate school, I studied different anode materials, and I used lithium metal as the cathode. So it's like, you call it a half cell, right? There's pure lithium metal would be a great electrode to use in lithium ion batteries, but we can't. It doesn't work. It forms dendrites, and it's not safe. That's part of the reason why we have lithium cobalt oxide and lithium iron phosphate and NMC and whatever, and graphite. A Japanese researcher in the 80s, I think, discovered graphite. It's the first in 70s or 80s. And then John Goodenough discovered the first commercial cathode material, lithium cobalt oxide, in the, I'm going to butcher the year, also the 80s or the 90s. Before then, lithium ion batteries were kind of a pipe dream, I suppose. They weren't safe because of the use of lithium, but in a testing environment for research, it's what you do. And so, yeah, you're studying your cathode, right? Which during the charging process, it loses lithium ions and they have to go somewhere. And so during the charging process of a battery, the lithium ions leave the cathode, your cathode material, lithium oxide, whatever you're studying, and they intercalate into graphite. Well, they can also intercalate into just lithium. Lithium will intercalate pretty well into itself. And it is a way to do two things. One is that you can reference very easily your voltages of your cathode that you're studying against the lithium plus, because that is the other electrode, the counter electrode, the anode in your case. And it basically provides you an infinite lithium source, right? It's lithium metal. It'll once you start discharging, the cathode loads up on lithium and the anode deintercalates, and there's plenty of lithium to deintercalate to make the process. It's like providing, it makes your cathode that you're studying the limiting factor, the limiting reagent, whatever you want to think of it as, which is what you want. You want to study its properties. You don't want to be limited by the other electrode. So using lithium metal, and in a similar way, when you do anode study, I use lithium as the cathode or the counter electrode, and so during charging, you're loading up your graphite or your silicon or whatever you're studying as your anode. You're loading it up with lithium coming from the cathode, which in this other situation is pure lithium. It has enough lithium to go and provide forever. It's pure lithium. So it's not limiting you. Whereas like, if I'm doing a full cell, lithium cobalt oxide or lithium iron phosphate or something, has some lithium in it, that lithium has to intercalate into the anode, but you're limited by how much lithium is in the cathode, and it's not pure lithium. So there's a finite limit of lithium available or something like, right? And that's just the reality of using an actual battery. You have a finite amount. That's why they decompose over time or whatever, and they lose some of their capacity or whatever. So the point of this is that when you use pure lithium, it's basically an infinite source. So, and it's a reference. It's the reference, right? Li plus. So it has both of those. It serves both of those purposes for you, and it allows you to study in that you call a half cell configuration. Allow you to study the properties of your material of interest. And just as a side note, I guess, just again, one of those sort of tribal knowledge things. That's also why, for example, in a real battery, the cathode's thicker than the anode. So the cathode usually is like aluminum current collector, and then a layer of whatever you have on it. So like practically a lithium ion battery will look something. Erase all this crazy Nernst equation stuff. A lithium ion battery will look something like a aluminum current collector, and then your cathode layer, which will be thick or whatever, and then you have your membrane, and then you'll have a copper current collector, and you'll have your anode, and it's usually much thinner. And that's just because this is for charging. This is your lithium source. And so if it's pure lithium, you don't have to have it so thick. But when you have a cathode, you have, lithium cobalt oxide or whatever, or lithium iron phosphate. You have a lot of this. You have a lot of not lithium. So you have to have a thick amount to be able to get it. And its capacity is lower. Its capacity is like 70 milliamp hours per gram or something. Whereas your carbon capacity is like 370 milliamp hours per gram. So it's like there's a capacity mismatch. So you have to have more of this than this to like have the equivalent amount of lithium. Otherwise, it's like one of them will be used up faster than the other one. So when you use lithium on one side, you avoid any issues about one getting used up faster than the other, something like that. So I hope that answers that question for you. I'm curious if the lithium ion systems are ever tested using split cell stacks with the divider being lithium metal reference. It seems like a good way to interrogate both sets. Um, that won't work because you need to have a permeable membrane so lithium ions can transverse between anode and cathode. People do fabricate systems in a similar way that you've described, Chris, which is where they effectively just jam a piece of lithium metal or something, platinum. Sometimes they use platinum for some reason. I think it's just convenience. Platinum is an easier metal to work. It doesn't corrode, right? Whatever. But they just jam a metal into the structure somewhere and use that as the reference. But you can't really divide the cell with lithium metal because lithium ions won't make their way through. Now, I know it seems like, well, if they just plate on one side and then go into the other, that probably works in theory, but not in practice because you'll get dendrites. You'll get a buildup on one side. I mean, it's basically dendrites are the main reason why lithium metal can't be used at all. Period. Is it doesn't plate evenly, right? Dendrite is like it's like those caves, stalactites and stalagmites, right? Where it's like a points or whatever. It's basically over time as you charge or discharge a battery that has pure lithium in it, it grows preferentially as like a spike, and then that spike will puncture through the membrane. Basically, it will force its way between anode and cathode internally. You get a short, and then the battery self-discharges, and then it's over. It's useless. The battery won't work. So lithium metal is not used practically. But in these kinds of research environments for testing your material, it's super great. It works quite nicely to get you some of those studies or whatever. So yeah, you weren't thinking in terms of the lithium metal as reference electrodes that could store them. Yeah, exactly. It's one of these, back to your sort of your general question about like, picking the reference electrode or whatever. This is actually one of these rare cases where, like, when you're doing a half cell reaction with a cathode or an anode and a lithium ion battery, and there's a lot of other struggles like getting the cell integrity, you have to have pressure with the electrodes, getting it constructed well. There's a lot of like things with lithium ion batteries and making them, and fuel cells too. That's like also a headache. It's like there's no part of electrochemistry that's not a pain in the butt, to be honest. But it's one of these rare cases where like the lithium does everything you need it to do, right? It's a great reference. It's a pretty stable reference, Li plus, and it's like an infinite source of your counter electrode for your anode or your cathode. So it's actually pretty useful. It works really nicely that way. If only it could be used in a real battery. It's kind of too bad, actually. Well, everybody, I'll give it another like 30 seconds to a minute if there aren't any other questions. It's been a couple of hours here, so I'm about at the point where I wrap this up. You know what I'm going to do, actually? While I wait and see if there's any other questions, you're going to watch 1 minute. I showed it at the beginning of this live stream here, but we have a podcast coming out, Alex and I, that we've been working on for quite a while, and I'm gonna plug it again because you're all at my mercy here because I'm the one with the camera and the microphone. So I'm gonna show this promo one more time. I hope that you all enjoy, and for those who are interested in a fun podcast that's some parts educational, but really not. It's a podcast. It's supposed to be funny and kind of stupid. And Alex and I make a lot of 90s movies references, and that's really my thing. It's really our thing. And we play games and we interview people, and it's gonna be a good time. So would you show up? Where is it? There it is. Okay. So here's this video. And then again, I'll check for questions, but otherwise this will be the end of it. So if I don't have any questions, take care, everybody. And I hope you enjoy this promo for our podcast.